All right, I'm going to hide that. Hello, everyone. Welcome back to Comp 3430 Operating Systems. It's been a long time since I saw you. Welcome back. Thank you for coming out. We are going to keep on trucking along today. What I want us to do is to spend a little bit more time taking a look at processes. So we're going to be looking at the API for exec and the API for wait. So these are the other parts of our process management API. And then we're going to move into taking a look at something called inter-process communication, or IPC. So I want to quickly remind you that the goal for me for the first 2 days is to basically make sure that you have the ability to use the mechanical API for managing processes and inter-process communication. And then on Thursday and Friday, we're going to circle back and we're going to take a look at what the operating system is doing underneath. So spending time taking a look at what data structures the operating system is using to facilitate things like managing processes and doing inter-process communication. So for now, it's just mechanical use of API, and then we'll start looking at the underlying what the operating system is doing after that. So some announcements before I really get into it. The first one is that I published the programming standards. They are up under the assignment subfolder for the course. The programming standards, you're not being assessed on programming standards for the labs. The labs were not assessing you on programming standards. Please be nice to Kyle. Please be nice to him with the code that you write. Don't just send him a bunch of garbage and then hope that he's going to give you something. Like format your code nicely, make it look okay. But for the assignments themselves, the graders will be assessing you partially on code quality for that. So that's where those documents really apply. The other announcement is office hours time. So I looked at the schedule on Aurora, and it's just like 3350 before this, 3170 after this, and then 4620 is also in there somewhere. And that's just your whole day. So the original office hours that I set were Tuesday, Thursday from 10:30 to 11:30, which is kind of like when 3350 is, when software engineering is. There is a half-hour break between classes this term. And so what I've decided to do is make my office hours just be immediately after this class on Mondays and Wednesdays. So 12:45 rolls around, 12:46 is office hours. Sorry, 1:45, 1:45. 1:45 is office hours. My plan for that is basically stay in the classroom for as long as there are people asking me questions in the classroom, and then go up to my office and just leave my door open for the rest of the time. But like I said before, my door is usually open. If you need to see me for something and the office hours just don't work for you, send me an email and we can schedule an appointment to guarantee that I'm going to be in my office. Or we can meet remotely or whatever. There are lots of ways that we can get together to talk about what you need. Yeah, are there any other questions before I get into it today? Yeah. If you have a lab, so with you mean with Kyle, yeah, you should go to the lab to talk to Kyle, to talk to him, because that's his office hours, and it can be anything about the lab. Like if you're stuck on a part, or you want to get farther than we are right now, yeah, go talk to Kyle. But attendance is not required. He's not checking that you're showing up. Yeah, you can go to any section you want. Yeah, yeah. All right, okay. It feels really warm in this room. It feels really warm in this room. I tried to turn the temperature down on the back, and I hope it takes effect soon, but it feels really warm in this room right now. And I'm sure that it's not just me feeling nervous up here for some reason. Okay, so by the end of today's lecture, what I am hoping for you to be able to do is continuing. So we started this last time, and we're going to continue working on this time. I'm wanting you to be able to write code that uses system calls to create and manage processes. So again, this is going to be the mechanical use of this API. We're going to talk about 3 system calls that are related to this. I'm expecting you to be able to write your own code that uses these system calls after that. I want you to be able to write, compile, and debug a basic C program. This is related to writing code that uses system calls. You have to compile that code to be able to run it, to see what the output is. But we're also going to take a look at reading binary files. So this is something that you maybe covered in Comp 2160, but probably not covered in 2160. So it's worth spending the time getting us all on the same page about how to do that. I want you to be able to write code where processes communicate through message passing via signals, pipes, and FIFOs. What we're going to find out very soon is that we have processes. We have the ability to create new processes with this fork system call. We can run other programs with the exec system call. But we're going to find out really, really quickly that they're all basically isolated from one another. And they can't talk to each other. We can't change a variable in one process and have it take effect in another process. So we have to have some mechanism for processes to be able to talk to each other. And this is where inter-process communication comes in. We want to be able to take one process and have it send information or events to another process. And we're going to take a look at a couple of APIs to do that. FIFOs are something that are related to pipes, but I'm just leaving that for now. We'll do that later in the week. FIFOs is something that you'll need for assignment 1, but it's not something that you need for the lab. So I want to defer that to later until we get later in the week. As I said last class, this is the 1 week where we're going to be doing things a little bit out of order just because I want to get you set up for the lab for this week. Everything after this week, we're kind of going to be like a week behind when the deliverable is. So it should be more structured, related to the way that the course schedule is set up. The last thing that I want us to be able to do is begin to compare and contrast the shared memory and message passing program models and their relationship as seen through the lens of synchronization. Those are all words that I assume everyone recognizes. We all know the word compare. We all know the word contrast. Those are good words. Shared. We all shared when we were little kids. We have memory. We all know what memory is in the context of computing. Message passing. We all know what messages are. We can pass things to each other. Programming models. We know what those are. Relationship is seen through the lens of synchronization. We can define all those words independently. The words that I have used that begins us on this already is the word blocks. So I used that word last time. I said I'm going to keep using it. The word blocks is a word that describes synchronization. And when I said that getChar is a function that we can call to get input, a single character of input. When I said that blocks, this is related to the idea of message passing. getChar is a function that we're calling. We're getting input on standard input, and it's we can squint our eyes and we can say that this is our shell passing information to a process that's running. But the idea here is that we're going to be able to take that idea and compare it to something called threads a little bit later in the course. So what the shell is doing, this is kind of where we left last time. The shell, this is at TCSH, this is that program that gets launched when you connect to Aviary. The shell is asking politely for the OS to do things using an API. The API that your shell is using consists of 3 system calls. Fork, take the process that's running now and duplicate it. So now there will be 2 copies of the same process running. 2 completely independent and separate copies of the same process running. The process that is one of those 2 processes is going to ask the operating system to replace itself with another program. So the thing that your code is asking the operating system to do is say, hey, here's the name of a program. I'd like you to start this code running in me. I'd like you to replace me with this. And then waiting for the child process to end. A shell, so when we were running commands on the shell, we could type something in, we'd press enter. It would show us the output from another program, but then when that program ended, we went back to the shell again, and we could start typing more stuff. The shell was waiting for that process to end. It was just kind of like sitting around in the background, waiting for that process to end. And when it did end, it printed out a prompt again, and we could start typing stuff into it to ask it to do more stuff on our behalf. Let's keep writing this C program that starts to do this. And I want to address a couple of things, because a couple of people have asked the same question, and I want to make sure that we can all hear the answer to that question when we do that. So let's take a look at this code. I posted this code up on the course website last time, so if you didn't get a chance to type it down, it's under yesterday's lecture, and you can get a copy of this if you want. If you want to start typing with me, I'm not connecting to Aviary today. I'm just going to run this on my own machine just to simplify things a little bit. In terms of like running stuff on your own machine, if you're running a Mac, you probably have like the Mac OS developer tools installed. I'm assuming you have the Mac OS developer tools installed, the C compiler, that sort of thing. If you're running a Windows machine, I would really, really strongly recommend, if you don't have this already, installing the Windows subsystem for Linux. If you haven't done that before, Kyle actually prepared a document describing how you can set up the Windows subsystem for Linux and then integrate it fairly nicely with VS Code. That is up on the course webpage under the resources section. That's worth taking the time to get set up if you haven't done that before. Even for outside of this course, it's just worth having that stuff set up. So let's remind ourselves about what's going on in this. Program. Why does this say bristles and toes? Wait, it's a message from Rob? For me specifically. Bristle toes, bristles toe, bristow. Okay, is that that's the joke? Okay. Yeah, okay, yeah, all right, thank you, Rob. Now I have to think of something to write back to him, but I guess I can write it tomorrow because he doesn't have class here tomorrow. So I'll think of something. Maybe you can think of something to help me with that. Let's remind ourselves of where this code is. So what this program does right now is it will launch a new process. We run this program, we inspected the output of PS, and what we saw was when we first launch it, there's one process that's running that's called hello. And then after we press enter, so we're in the parent process, press enter to proceed, getchar is blocking. It's halted the program's execution there, and we've stopped. Once we hit enter, we've run the next line of code there. Child is equal to fork. Fork is this system call that's duplicating our process. Duplicating a process means literally that. So think back to Comp 2280. When you're running code, you have this idea of a register that's the instruction pointer, right? We all know what instruction pointer is. Quick thumbs up. Yes, good, 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 good. We've got this idea of an instruction pointer that says this is the instruction you're executing now, this is what you should execute next. When we duplicate a process, we're duplicating this down to the instruction pointer level. So C code, remember, C code is a high-level language. C is a high-level language that we compile down to assembly. When we get to the point of executing a hardware interrupt, so when the fork system call ultimately goes back up into the operating system, we do the mode switch. We do that switch into the system mode. When it returns, the result is that we've got two independent processes that are running. They both have the same code. They both have the same code. They both have the same copy of code, that they're physically separate from each other in memory. They both have the same instruction pointer. They're both pointing at the same instruction. And so they're going to start proceeding in the same sort of order. So we duplicate it. Stuff starts happening. We've got the instruction pointer that's pointing at the same instruction in both of these copies of code. They're going to start printing stuff out. This variable we've seen, this child variable, is different between both of those processes. One of them has a value that's non-zero. The other one has a value that is actually 0. And the value that's in this variable is what tells us, this is our code now, this is what's telling us which one of these is the parent process, which one was the original, and which one is the copy, which one is the child process. The one where child has a non-zero value is the parent process. That's the original one. That's the first thing that was launched when we started running this process. The one that has a value of 0 here is the one that was duplicated from us. This is our copy. This is our child process. When we've got these two processes now, they're going to keep running. Instruction pointer points here. When we run fork, instruction pointer is pointing here. When we've got printf, this branch now in each of these two copies of the process is going to behave differently because the value that we have in child is different between the parent process, the original one, and the child process, the one that we duplicated. So the path that this is going to, each of these are going to take is different through here, and then eventually they will both exit, they'll both end, they'll both terminate, and that's kind of the end of that program. One of the things that that some people were asking about, I've had this a couple times, is that when I run hello, and I wasn't able to actually duplicate this in my own examples, but other people were able to do it, is that sometimes when I run this code, sometimes when you run this code, and you will eventually see this, sometimes when you run this code, the parent stuff prints out first, and sometimes when you run it, the child stuff prints out first. This is kind of the expected behavior. We actually can't know which one is going to get to go first. After the fork system call is made, we have two processes. They are running independently from one another. We're going to see this when we get to scheduling processes, but the operating system's job is to try and make it look like these two processes are running concurrently. So concurrently means that it looks like they're running at the same time. It looks like they're running at the same time. Concurrently means it looks like they're running at the same time, even though they might not actually be running literally at the same time. It just looks like they're running at the same time. And the operating system's job is to make decisions about which one of these processes actually gets to run next. So that's expected. We can't know if the parent's going to run first or the child is going to run first. Just one of them is going to run first. We don't know which one it's going to be. The other thing that I want to pop in here is that these are two completely independent processes. They are related to each other, but they are not sharing anything. They don't share anything other than the code. And the way that they're sharing the code is that it's a copy. It's a copy of the code in two different places in main memory. So what do I mean by that? I'm going to say this. I'm going to say, I'm going to put a char in here, char value. And in the child process, I'm going to write this. Value is equal to A, and in the parent process, I'm going to say value is equal to B. Do we all agree that A and B are not equal? They're not equal values, right? Yes? Okay. I'm going to put an infinite loop in both of these. I'm going to say while one, printf, child process. I'm going to make this really, really clear. Child value is %C. Okay, and I'm going to copy this. So in Vim, to highlight lines and then copy them for copy and paste, you exit insert mode. You hit escape on your keyboard. You can enter something called visual mode. So I pressed V on my keyboard, and you can see that there's visual at the bottom there. And then if you start using your arrows to move around, it's going to highlight stuff. So highlight what you want to copy or cut. And then to copy in Vim, it's called yanking. It's Y. It's the character Y that you press. So I'm going to press Y on my keyboard, and it says 3 lines yanked. So I've copied them. They're like on my clipboard right now, and I can paste them if I want to. To paste something, you use your arrow key to move to where you want to go. You might need to make some space. So I'm going to enter insert mode, and I'm going to add a new line after the line that I'm currently on. And the way that you do that is by pressing O on your keyboard. So I've added a new line, and I've entered insert mode at the same time. And I'm going to get immediately out of insert mode, escape, and then I'm going to press P to paste. So P is going to paste that value that I yanked before. And I'm going to use some formatting options here. I'm going to use the greater than symbol twice. I press it twice, and that's indenting it for me each time. So I'm going to print out while one, printf, and I'm going to delete this, and I'm going to say parent value is %c, and it's going to print out the value of value. I'm going to stop here. I'm going to stop here for a second, and I want you to take the time to think about this, predict what the output is going to be. I'm not going to ask for your feedback, but I'm going to ask you, I want you to just stop and think about what you think the output is going to be. We've got 2 infinite loops. There's 2 things that you should be thinking about when you're trying to decide what the output is going to be. One is, what is the output going to look like in terms of, does the parent get to print everything first? Does the child get to print everything first, or is it something else? And what is the value going to be in each of those? Feel free to talk to your neighbor. There's a lot of nice people in this room. I recognize a lot of people. They are all generally very nice people. OK, do you have an idea? Do you have an idea in your head? OK, I'm going to hit enter. And I don't know. I want to see reactions here. I want to see reactions. So like, you know, total anguish if you're really wrong, or like, yeah. OK. So I'm glad I've got my machine plugged into power here, because this would just kill my battery if I just left this running for any longer. My fans are spinning up right now because there's 2 processes that are running at 100% CPU just printing this out on the screen. And I'm just going to let it go. So the first question that I asked was, which one prints first? And similar to what I said before, we can't predict which one's going to print first. That also applies here. I mean, the first one that got to print is gone. I can't get that back anymore. But the second half of that question is, does this one finish first before this one starts? Or does it just kind of like do the opposite? Or what does it do? And the answer here is, it's kind of like just switching back and forth between the 2 of them. These 2 processes are running concurrently. They are running at the same time. One of them prints something, the other one prints something, It might print 2 lines, then the next one prints something. It might print 2 or 3 lines. It's usually just printing 1 at a time. It kind of looks like they're switching back and forth after each print statement. But I want you to remember that this printf statement, this while loop, when we compile this, this is breaking down to instructions, individual instructions. The while loop is like branch if not 0, something like that, branch if 0. And the branch that it's going to is back up to the top. Our printf statement is going to turn into a huge mess of assembly language instructions because it's doing a bunch of string processing. Cue like sudden nightmares about comp 2280 and string processing. It's doing a bunch of string processing stuff, like to find these percent symbols and then replace them with values that happen to also be on the stack at the same function call that you're in. Yeah, there's a lot going on there. These are breaking down to instructions. Printf, so I'm going to use a word here that I haven't used to describe anything yet, but I will use it throughout the course. Printf has output that is buffered. So buffered is a word that I haven't used before. I will use it throughout the course. Buffered means it's going to hold on to its output until it has enough output. Printf breaks down to a lot of different instructions, and these processes are switching around in like not mid-instruction, but like after an instruction has completed. And it might be somewhere in printf, but printf is holding on to its output until it's got enough. So what we're seeing here is that printf is getting an entire line of outputs every single time. So it holds on to just enough output until it has enough, and then it prints it, and then we're switching to the next one. The other thing, I'm going to stop this because it's kind of hard to see it. The other thing that I'm asking about is what effect does changing the value of this variable called value in each of these branches have? Value is equal to A, value is equal to B. Each branch is doing something different. The child is setting it to A, the parent is setting it to B. I'll let you scan up here, but the child is always A, and the parent is always B. This isn't an effect of like switching rapidly between the two of them. The value that value has is a bad name. I can't even call it like char, because it's just also going to be a terrible name. The value that value has in the parent is completely separate and independent from the value that value has in the child. They are two completely separate processes. Let me even do it this way. I'm going to change this code to say that value is equal to C. I'm going to say that it's going to print out value is equal to, change this value to A in just the child process. I'm going to make it, I'm going to give you a second to think about it, predict what the output is. I'm going to put 10 seconds on my timer here. Talk to your neighbor if you want to. Okay, I'm going to run it. I'm going to hit enter to proceed here. These are entirely separate processes. They are completely distinct. They have the same code. They have copies of the same code in different places in memory. This variable called value in memory has a different location in the parent process than it does in the child process. They're just in different places in memory. They're not referring to the same physical location in memory anymore. So changing one isn't going to change the other one. There's not a clear way for us to communicate between these two processes. So the two things that we're taking from this now are, we don't know what the order is. We cannot predict what the order of execution is. I'll get to you in just a second, okay? We can't know what the order is, whether the child process runs first or the parent process runs first. And the other part of this is that, yes, we can have variables that are the same. It's the same program code that's running, but they are completely separate from each other when we're actually working on these two pieces of code when they're running as separate processes. Yeah?
The address of the program code would be the same for the two variables? Like in actual memory, it's different, but...
So that's a great question. Here's what I'm going to say. I'm going to print this out. Address of value is %p. It's a pointer that I want to print out. And I'm going to use address of value. And I'm going to say get char here again. I want to block. I want to actually be able to see that before everything else comes out at the end. So I'm going to make hello, and I'm going to run it. I'm going to press enter. This is the first one that we're stuck at right now, right here in this program. I'm going to hit enter. Oh, okay. So this is kind of like, hey, that's not what he just said. That is not at all what he just said. This is virtual addresses. These are virtual addresses. And these are different from physical addresses in memory. Every process has its own virtual address space. We're going to get to virtual memory later. For now, even though they are the same address, they're still located in physically different places in memory. Okay? Does that answer your question? Okay, good. All right. So I want to do two more things here with this code. I want to cause a program to be executed that's not the code that I've just asked to be executed. So I want to cause another piece of code to run. And I want my parent process to wait for the execution of that code to finish. The general strategy that code uses to accomplish this is that we've got a main process that duplicates itself. It forks a child process. And then the child process will execute code. It will ask for other code to be replaced in its address space. And the parent process will wait around. That's what our shell is doing. We press enter, it forks, it execs something in the child process. The parent process waits around. The child process finishes and returns control back to the main process again, the parent process. So let's do that. I'm going to hit Control-C on my keyboard over here to terminate that code. I don't really care to see that infinite loop anymore. The function, the system call that you're using to execute code is called exec, and there's a family of exec functions that are all interrelated to each other. I'm going to say man exec. This is why I'm usually putting numbers in my manual page requests. So there are overloaded names of things in Linux and Unix systems. Exec is an overloaded name. Exec is the name of a program, but I want to know the API for exec. So I'm going to quit this, and I'm going to say man2 exec. I'm going to say man3 exec. And this is where I'm going to actually get the API that I want. I'm going to zoom this in. I'm going to quit this. I'm going to man3 exec again, just to make sure that we've got it filling the screen here. There's a family of functions that are all starting with this prefix of exec. Exec L, LP, LEV, VP, VPE. There's a lot of stuff that's going on here. I am going to straight up tell you that the one that you should use is called exec VP. That's the one that you should use, is exec VP. Exec VP gives you the ability to pass a string. The string is a file name that represents the program that you want to have this process be replaced with. And then the second argument here is a null terminated array of strings. So the last entry in this array is the null literal. This is a null terminated array of strings that get dumped into argc and argv in your main program, in your main function. So when you are writing your main function, you're usually writing int argc char star star argv. This is argv. This is argv. This is that exact same argv. So this is how we're passing arguments to something when we're having it execute in our code space. So I'm going to zoom out of this. I'm going to do this by just hard coding stuff. I'm just going to hard code things to demonstrate how to use this function. The way that I'm going to hard code this is I'm going to comment out my infinite loop here. Actually, I'm going to leave the infinite loop in. I'm going to leave the infinite loop in the child process. The child process is the one that I want to actually run this other program. I'm going to be using exec VP here. Exec VP does have an integer return type that can tell you when things have gone wrong, like exec VP failed to run for some reason. But exec VP is a function that generally does not return. It never returns. So I'm going to write here exec VP. The first thing that I want to pass to this is bin cat. So I just want to run cat again. The args array that you put in here is going to be an array that consists of the arguments that you want to be passed to this program. The args array has to follow kind of a special format. The 0th entry of the args array is the name of the program. So if you're running cat, it would be cat. Or you could make it whatever you want. You could call it dog if you want to. It's what the program will believe its name is. It's what the program will believe its name is when it's executed. Arguments 1 to n minus 1 are the actual arguments. And these are the command line arguments. So when I run cat, what I had been doing before was put nothing, and it just reprints stuff. I'm going to hit Control D here. If I cat hello.c, it's going to print out my file. If I give it a file name, it prints out my file. It concatenates that file to standard output. The last argument is the literal null. It's a null terminated array. So it's not just a null, it's an array of null terminated strings that's terminated itself by a null. So here's what I'm going to do. Char args, it's an array, and I'm going to just make an array literal in C here. The first one that I want to put in here is bin cat. The second argument that I want to put is the name of this file. And the third argument that I want to put in here is the null keyword, so this literal null. And I'm going to pass args here to exec VP. I'm going to make this and hope desperately that it is what it's supposed to be. Good, OK, the compiler did not complain. And what we've got here right now, whoops, what we've got here right now is effectively run bin cat with hello.c in the current directory. So if I run bin cat hello.c, this is what I'd expect the output from that to be. I'm going to comment out this so we can see the effect of this happening. I'm putting a semicolon there just to leave the infinite loop in the parent process. But I'm going to comment out the printf because I want to see that the cat has actually worked. The call to cat has actually worked. So I'm going to make hello again. I'm going to run hello. We're blocked right now on this in parent process, press enter to proceed, and then we're going to be blocked again immediately after that on the address of value. I'm going to press enter again. In the parent process, child ID is 901510, and the parent process is just like hanging out here. I hit enter again. Okay, I had to hit enter twice. That's weird. I had to hit enter twice, but then worked. It actually worked. I'm going to press PSA. And what I want us to see here is that hello is running. This is the parent process still that's running. There's this other process that's called cat, and it's got this special mark here. It's got square brackets around it. It is defunct. And it has this special character here that says Z. I've tried really hard to get this to happen in like previous offerings of this course, and I'm just delighted that it's worked out this time. This is our child process. So 90510, if you remember briefly, we printed that out. That was the process ID of our child process. It's finished. It never actually got to this while loop. Exec VP, if it works, if the call is successful, it never comes back to our code. What we've done by calling exec VP is effectively say, I would like you to take the program that's here at bincat. I'd like you to read that file. I'd like you to replace all of my code with that code and set the instruction pointer to be its main function, and then start running it. The while loop never actually gets to execute because our code never returns back to our code, because cat has no idea that we called it. It just knows that it was called by something. Cat right now is in what's called a zombie state. Z is for zombie. Z is for zombie. Z is for zombie. It's a child process who has died and its parent hasn't reaped it yet. This is really awful terminology. It's a child process whose parent hasn't reaped it yet after it has died. And so what does that mean? A parent process hasn't reaped its child after it's terminated, after it's ended. That's the second part of this. Our process is not actually waiting around for this child process to end. It's waiting around, but it's an infinite loop. It will just wait around forever. If I commented this infinite loop out completely, it would just end. Like the child process would end and the parent process would end independently. But we may actually want the parent process to wait for the child process to end so that the parent process can start doing something again, like our shell is doing. We get a prompt, we can type something in, we press enter, the shell makes that program start, but when that program finishes, the shell comes back and it prints out another prompt so that we can start typing stuff in and ask it to do more things for us. The second half of this is called the wait system call. So here again, wait is the name of a program or a shell built in. So I'm going to type man to wait. Wait is wait for a process to change state. Wait for it to finish. We're going to be using the first version of this, wait w status. There's another version of it called wait PID. Wait PID lets you specify the process ID to wait for. Wait says, wait for any child process that I've created. That means that if you launch 5 processes, so if you call fork 5 times, wait will just wait for any of those 5 processes to finish. If you want to know that you've launched 5 things and all 5 of them has finished, you have to call wait 5 times. That's a nice loop structure. That's a nice loop structure. Wait PID gives you the ability to wait for specific processes by ID, and it will say if this process is already terminated, then it just returns immediately. If not, we'll wait for it. So I'm going to have my manual page open here, and I'm going to change this to be, let's wait for our child to finish. The way that we wait for our child process to finish is to use the wait system call. I need to include these includes at the top here, so sys types and sys wait. So I'm just going to quickly go back to the top of my file. In Vim, you can escape insert mode, and you can hit just lowercase g twice, and that takes you to the top of the file. I've got sys types here already, so I'm going to say number include syswait.h. I'm going to write that, and I'm going to go down. If you hit Shift G, that takes you to the bottom of the file. I'm going to wait, and what I'm going to say is just wait null for now. The argument that you can pass into this is a pointer to an integer. And if this is a non-null pointer, you can get back the status of the process after it's finished. So if you remember from 2160, fgets, for example, returns a value. The value that it returns might be an error. This is kind of the same idea. I want to know what error state the process that I'm waiting for left in. Similar to get char, wait is a blocking system call. Code stops running here until an event has happened. It blocks. It's going to halt. It's going to wait here until that event has happened. The event that we're waiting for, I'm going to make this an asterisk here. A child process has ended. Not all child processes, just a child process. We are only launching one here, so we only have to wait one time. But if there are others, we need to wait for them as well. So this says wait until that child process has ended. I'm going to quit my manual page here. I'm going to make hello again. We don't have an infinite loop in the parent anymore. We have exec in the main, in the child process, in the duplicate. I'm going to put a printf here after the wait. I'm going to write parent. Child has ended. I'm going to make that again. I'm going to go back up, and I'm just going to comment out this get char. I don't care about seeing that address anymore. It's OK for that to go away. The get char, we had to press enter twice there because there were two processes running, and each of them were waiting for input on get char. So I had to press enter 2 times, one for each process. This one, I only have to press enter once because it's before the fork. There's still only one process running with this code. So I only have to press enter 1 time here. I'm going to make this again. I'm going to write this again, and then I'm going to make it again. I'm going to run hello. We're blocked right now at that get char. We're just about to run fork. We're going to print out this PID is. We're going to print out the value, the address of that value. Then we're going to go into this branch. We're going to print out in the child process. Exec VP is going to print out. It's going to run cat. Cat is going to print out hello.c, and then it will terminate. Once it's finished, it just ends. It's over. We're going to make sure that this statement, printf, parent child has ended, that will not print until all of the output from cat has been produced. We are synchronizing. OK, so this is that keyword at the bottom, beginning, synchronizing. Looking at the differences, compare and contrast. Oh gosh, compare and contrast. I can't even remember all the words, and I'm just going to bring it up because I want to be accurate here. Compare and contrast the shared memory and message passing programming models and their relationship as seen through the lens of synchronization. This is synchronization. I am making sure that this statement, this printf statement, will not print until after something else has happened. I am synchronizing these two processes now. This should be the last thing that we see, because I'm pretty sure that after that, we've got exit success. So it just terminates the program after that. So I'm going to hit enter. I'll zoom in here. I'll hit enter. We've got the output from cat. It never returns, so it never gets stuck in that infinite loop. The parent has waited for the child process to end. So after it's finished printing out the content of this file, it exits. The parent says the child is ended, and that's it. OK. I'm going to hold here for a second. If you have any questions, this is kind of where this stops. Yeah. To launch the processes? To watch them, the command that I'm using is PS. It's really hard to see. I'm sorry. I should switch. That's not going to help me here. I should switch this to a light theme, I think. That did not help. I switched it to light, and it didn't do anything. It's PS, and the option I'm passing is A to print out all the processes that are under my user ID. Yeah. If you just do PS, it's only going to print out the things that are in this shell right here. A says print out everything for me. And then the other options I said were FUX. F is for forest, U is for user, and X is for like extended output, which gave us a lot more stuff than we were expecting to see. Yeah. When would it hit it? Yeah, so the only way we get here is if exec VP fails. And reasons for failure might be things like the program doesn't exist. So if I like type in the wrong value for what the path of this file is supposed to be, exec VP will be like, no, it doesn't exist, fail. And you can inspect the error code there. But successful means it's just not going to ever come back to our code. Yeah.
If we didn't have the wait, when exec CP is like running and like all like the lines are being printed out, would like one of like in the middle somewhere be the parent child line?
Yeah. So the parent output. So the question was, just repeating it for everyone to hear. The question was basically, if I commented this wait line out, would this line start to show up somewhere else? Like, could it be in the middle of the output from cat, or could it be at before the output from cat, or anywhere in between? And the answer is yes. If we don't synchronize the two processes with wait, then it's going to be unpredictable. We can't know where it's going to be. Yeah.
Before the wait.
Yep.
The printf already printing somewhere, right?
Yes. So let me go up here. If I can. I never know how to use this keyboard. This is a laptop. This is a laptop, and I just always have it on my desk. It's always on my desk. I don't actually bring this anywhere. I bring it to class. And then when I start to need to use the keyboard, I don't know how to use the keyboard, because I have a real proper keyboard on my desk. So I'm going to do this. I'm going to use a program, or an option here that's called pipe. I'm going to pipe the output from hello into less. And this is also not going to work the way that I want it to, but I'm going to do it anyway. This is taking the output from hello, and it's taking the output from hello and giving it as the input to less. Less is something that's called a pager. It's just going to like capture what our output was here. So when I press enter, we're going to get a bunch of output from these two things that are kind of like separated, but the order here is it's not clear which one is going to get printed first. It's just going to be based on whichever one happens to get run first. Okay, so I'm going to switch back here. We've got about 20 minutes left, and I want to make sure that we get to the next couple of parts. So to summarize what we just talked about, these parent and child processes they're independent from one another, but we can synchronize them a little bit using that wait system call. The parent and child processes are independent from one another because our operating system is managing them as two completely different things. Even though our addresses were the same for that variable, they're the same as virtual addresses. Again, we'll get to this later, but they're the same as virtual addresses, but they're physically located in different places in main memory. They're related, but they don't share any memory. Changing values in one doesn't change values in the other. They sort of share standard input and standard output, though. So we can see the output from exec VP of cat being printed in our terminal, and all the other printf statements from the parent process. I had to press enter on my keyboard twice in the same terminal when we had two different processes. They're sort of shared, and we're going to see that other files are actually also sort of shared between these two processes. But that's a discussion for another day. The other question that we asked last time was, once we've got this exec happening, what is the operating system doing? And to answer that half of the question, we kind of have to take a step back here. What even is a program? What even is a program? And the way that I want you to answer this question is, what's the result of compiling code? What do we get as output from compiling code? Take 10 seconds to think about this. This is not a high-level question. This is really not a high-level question. I'll highlight that part specifically. It's a file. It's a file. It's just a file. It's filled with binary and like assembly language instructions that have been compiled down into bits. But it's just a file. It is just a file. There's nothing special about this. It's just a file. It's the same as the Hello World source code that you wrote as a file. This is also just a file. It's just a file. A program it's literally a file. Yeah, there is some special stuff about it. Like you can't try to run source.c. You cannot run source.c, but you can run something that's a compiled program. But it's still just a file at the bottom of this hierarchy. In Linux and a lot of other Unix systems, the file format for these files is called ELF. It's an ELF formatted file. I'm going to open this up. This is a link to Wikipedia. ELF is a format. It's a binary format that basically takes source code. Sorry, I'm gonna walk back on that in a second. A compiler takes source code and ultimately emits ELF. ELF is a format that an operating system can read and start to actually do stuff with. There's another format called dwarf. ELF is the executable and linkable format, and dwarf is the debugging thing. So when you do -G on Clang, you're getting dwarf files as output to go along with it. Yeah, ELF and okay. It's a structured, formatted binary file. That's the main takeaway here. It's a structured, formatted binary file. If a program is a file, how do you read a file in C? Let's take a couple steps back. Do you have a question? Okay, let's take a couple steps back. Welcome to Comp 2160. By the end of today's lecture, you should be able to read some files in C. Reading files in C basically starts with include stdio at the beginning so that you get nice functions like fopen check the value that was returned, because we always check the values that are returned by these functions. We always check the value that was returned by the function. And then we use functions like fgetS and fgetC. It's good. We're good. Yes. OK, wait. Hold on a second. fgetS and fgetC are not really like binary data. They're not binary data. fgetS is file get string. It's literally string. fgetC is get char. It's a character. Yeah, that is data. It's binary in the file itself, but that's not going to be super helpful to us. An ELF formatted file is a binary file. It's a binary file. So we're going to need to treat it as a binary file when we start to open it. And when we're starting to think about what does the operating system do? How does the operating system read this ELF file? Where do these functions come from? And this takes us back to this diagram. Where do fgetS and fgetC actually come from? Where are those functions defined? And the answer here is they're in that green semicircle. They're in the GNU-C library. Our operating system, again, probably a lie you got told in 2160, fgetS is not asking the operating system to do anything. This is asking your standard library to do something. Your standard library then is going to use this system call interface to actually do stuff. In this case, your standard library is going to use system calls to ask the operating system to get data from disk on the virtual file system, part of the interface. I still want us to do this, though. I still want to take the time to read some binary files from disk. I want to read something from disk, and I want to do this in a C program. It's not doing what the operating system is doing, but it's still going to give us an idea of how to read some binary files. So the way that I want to approach this is I want to use a format that is a little bit more approachable than ELF. This is an exercise for the reader. This is an exercise for the reader. But I want to start by doing something that is a little bit more approachable. And the little bit more approachable thing that I want to do is I'm going to go to Wikipedia again. And I'm going to be looking for the BMP file format. Do we all know what BMP is? Bitmap? I like this little program here. I can't make it any bigger. It doesn't zoom in. It doesn't zoom in. You're just kind of stuck with what this is. I wonder if I can make it bigger this way. Yes. Now I'm suddenly realizing that many of you may never have used this program before. Has everybody used Paint before? Yes? OK, good, good, good. OK, good, good. I'm not as old as I thought I was. So I want to take a program that can produce this BMP file format. And then what I'm going to do with this is I want to start going through this structure. Wikipedia has a lot of good file format descriptions. And we're actually going to start with this bitmap file header stuff. We're going to start with this bitmap file header stuff. Bitmap file header, this table is going to describe to us what certain bytes are at certain parts of the file. And then we're going to read through them and actually get this data out of the file so that we can start thinking about how to work with binary formats. So first things first, we've got to draw a picture. We have to have a bitmap file to work with. I'm going to draw a picture of my bitey cat. He's got stick legs. He comes and walks on me, and he's just got like stick legs walking into my tummy. So I will give him stick legs, and he's got this nice tail, and he's got yellow eyes, and he's got a little pink nose. This is a bad picture. Oh, that's okay. And he's got whiskers. Okay. I'm going to fill him in here. He's a black cat. The whiskers are gone. It doesn't matter. I'm going to save this. I'm going to save it as a bitmap file. I want to actually save it as a bitmap file. I'm going to leave this as a walter.bmp. This is going to pop into my downloads folder. And so I'm going to move it into the directory that we're starting with. So I'm going to quit this program. I'm going to move downloads walter.bmp here. So it's there in my current directory. I'm going to start writing a program to start reading this. So I'm going to start by doing one thing here. I want to do hex dump. Hex dump is a program that prints out binary files in hexadecimal. It prints them out in hexadecimal. It prints them out in hex. I'm going to say hex dump. I'm going to pass this option C, uppercase C, and I'm going to print out walter.bmp. This is the bottom part of that file, but it's several hundred kilobytes in size. So I'm going to run this again, but I'm going to pipe it. I'm going to pipe the output of this. I'm starting to use terms here. I'm piping the output of this into another program. The program that I'm piping the output into is head. Head is a program that will print out the first some number of lines of output and then just get rid of the rest of the output. So I'm going to pipe this into head. And what I really want to see here is these bytes. I want to see these bytes. This is the location in the file. So this is it starting at location 0 in the file, the very beginning of the file. This is the very first byte in the file, the second byte, the third byte, the fourth byte, and so on. These locations in the file here, these are hex locations, so they're not like 1 through 10 or 0 through F. Let's take a quick look at my great picture again. Let's take a quick look here at this bitmap file header. And what we can see is that at offset hex 0 or at offset hex or at offset decimal, there are 2 bytes, and those 2 bytes are the header field used to identify this as BMP. On Windows 95, 3.1, NT, etc., it is B and then M. The symbol's B and then M. I'm going to go back here, and what we see in this output from hex dump minus C is that the first 2 symbols here are B and then M. Those are the 2 values that we want to get out of this to represent what this file is. I'm going to start with this. I'm going to make a new file here called readbin.c. And I'm going to just start typing some stuff in here. So I'm going to say int main void. I'm going to hard code what the name of this file is. So char star fname file name is equal to untitled.bmp. And what I want to do is I want to start using some functions that that we know about. So the functions that I want to use here are open. I'm going to say man to open again. I want the system call that is the manual page. I'm not using fopen here. I'm not using fgetS. I'm not using fgetC. I'm stepping down to a lower level and using the system calls directly. So your standard library is calling these system calls. We're just going to start calling them directly ourselves. I'm going to include systypes. I'm going to include sysstat. I'm going to include fcntl.h. And then I'm going to call open on this file name. So I'm going to say open. I would like to open file name. I'm going to have an integer value, and I'm going to call it fd. Fd, when I'm writing fd, I'm saying file descriptor. File descriptor is a specific term that's used to say that it's an integer value, but it is a unique reference to that specific file. It's a unique reference to that specific opening of that specific file. The arguments that I want to pass to this are the name of the file and then the flags. The flags are defined in this manual page. I'll let you read that on your own. But the thing that I want to pass here right now is, oh, read only. I don't want to write this. I don't want to make changes to the file. I just want to read it. But again, read this document, the manual page, to see what the other options are for opening files here. I'm going to open this. And then what I'm going to do, I'm going to quit this. I'm going to do man2 read. Read is another system call that takes as input a file descriptor, so what you get back from open. It takes a void pointer to a buffer. This is a fancy way of saying an array. It's an array. It's taking a reference to an array, and then size t count is how many bytes do you want to read into that buffer? How many bytes do you want to read into it? I'm going to make a new buffer here. The buffer that I want to make is using a specific type. I'm going to go back to my wiki article here. This first field is defined as 2 bytes. And the 2 bytes that we're getting out of this are characters B and M. I want to treat these as 2 different symbols. I want to treat them as 2 different symbols as opposed to treating it as one single value. So I'm going to create an array to represent that of 2 bytes. The array will be of size 2 bytes. When I'm working with binary files, my approach to doing this is to use standard integer types. So in Comp 2160, you might have used unsigned char to do something like this before, to represent a single byte. But char can be different from system to system, and long can be different from system to system, and short can be different from system to system, architecture to architecture. There's another library that you can use called stdint. So I'll add this here. Remember, include stdint. Stdint is giving you the option to use types that are of this format, uint8t. So unsigned integer that's 8 bits wide, underscore t for type. There are other ones that are like int16t, 16 bits wide, but it's a signed number. uint32t is 4 bytes, unsigned integer. I'm going to say I want this to be uint8t. I'm going to call this header, and I want it to be 2 bytes in size. That's what this header is supposed to be. I want it to be 2 bytes in size. I'm going to now read. So I want to include unistd here. So I'm reading my manual page, and I see that I need to include unistd. I want to read from the file descriptor that I just opened. I want to read into header, and I want to read 2 bytes. Read as a system call, kind of like fgetS, start at the top and work your way down. So we're opening this. It's opened to the beginning of the file. I'd like to read into this 2 bytes, and then I'd like to return exit success. And to get exit success, I need to include stdlib.h. OK. I'm going to make read bin and hope that there are no compile errors here. OK, good, good. Every single time I do this in class, live demos, it's just like, oh, I really hope there's no errors because my, me old person Vim doesn't show squiggly underlines when there's a syntax error, and I'm just really, really hoping. I'm going to run this, read bin, and nothing happens. Great, excellent, because there's no output. There was no output in this program. There was no output. I'm going to quickly, we've got 2 minutes left, so I'm going to quickly open, whoops. I'm going to quickly open a new Vim. I'm going to make a makefile here right in front of you. I'm going to make a makefile. You are given explicit permission to copy this makefile. Don't make your own makefile. Just use my makefile. I'm going to say CC is equal to clang. C flags is equal to W all, W pedantic, W error. I think it was W extra. I think that's the other one I've got on there. Lots of errors. W all, the lie we told you in 2160 is that W all does all the warnings. No, it doesn't. There are more warnings. There are even more warnings. CC, clang, and C flags with all of this extra stuff, these are actually variables that make uses internally. So you'll notice that I was using make before, but I didn't have a make file, and it was still just working. Make knows how to build a lot of different program types based on languages and extensions. So it knows how to compile C programs, and it uses these variables, CC and C flags, to define the rules that are used to make those things. I'm going to say .phony, and .phony is for clean. This says that there might be a file that's called clean, but treat it as a target anyway. And then I'm going to say rm-f something. I'm going to say all, and I want bin read. And that's it. I'm not going to actually put bin read in there. I'm not going to define it because make knows how to build C programs. It already knows how to do that. So based on bin read being a target and binread.c being in my directory, it knows what to do. It already knows what to do. The other thing that I want to add here, though, is -g. I want to add to my C flags -g because I want to get debugging symbols. I want to be able to debug this program. I want to run it through my debugger. I learned the other day that -g is not the only option. You can do things like -g4 and you get more debugging symbols than you did before. I didn't know that. But I'm just going to stick to what I know, which is just to say -g. I'm going to change into this directory, and I'm going to make, there's no rule to make target bin reads. I need to add it anyway. I'm a bad person here. Bin read, binread.c. That's what I want to say. Thank you so much. Okay, so we're out of time. Bin read, read bin. Nothing to be done for all because I already compiled it. Make clean, make. Okay, so we've got that. Now what I want to do very, very quickly here is launch my debugger. I'm going to launch my debugger on read bin. When I enter this, you can expect to see this if you're running this on Aviary, this module not found error. Just ignore it. LLDB is scriptable with Python. We're not doing that. You're not expected to do that. The stuff that's necessary for it is not installed. You can safely ignore that. We're in this target read bin. I'm going to set a breakpoint on main. I'm going to run my program. So breakpoint main says set a breakpoint on the function that has this name. R says start running it, and then it's starting to run. I'm going to press N to go to the next line, the next line, the next line, and then I'm going to print out p header at 0. And what we get back is nothing. I have taken up 2 extra minutes of your time. Thank you for that. We'll come back to this tomorrow. And I hope you have a good night. Bye, everybody.